welcome to Geek Orthodox. I'm Father Justin, Geek from my youth. It's been a while since we did a World of Code episode of the Geek Orthodox podcast. That's been mostly accidental, but there's been a little bit of method to the madness. We just finished a major arc of the podcast, which culminated in an examination of two of my all-time favorite pastimes, and the impact of the world of code on them, namely reading books and playing games. And we saw how code, by its nature, enabled us to take various elements of these pastimes, for example, the increasing complexity and mathematical computation that is involved in playing games and simulations, and in taking kind of the map that was the kind of foundation for Tolkien's world building, and creating a map and taking all of the burden of calculations off of the player in order to really enable agentic engagement with the world that was being built in code. Now, my goal in selecting code's impact on narrative and games as kind of the culmination of this arc of the podcast is, of course, not to say that that's the most significant impact that code has had on our world. Rather, it's to give this, to present them as a representative sample of the ways in which code naturally impacts the world in which we live, and to take for that sample an area which I know reasonably well, having engaged in both a lot of reading and gaming, both before and after code started to have an impact on those areas. So now that we have established a representative sample, if you will, of the way in which code can impact the world in which we live, I'd like to dig a little deeper, and in this next arc of the podcast, look at how the inherent complexity of code has a fairly significant impact on us. And this will take us ultimately into AI. But before we get to that level of complexity, let's go all the way back to the foundation of the computer, the most basic component of the computer, namely the switch. As you will recall, computers are really just a bank of switches that are arranged in different ways so that they can turn on and off, do basic logic. And that simplicity is also, to some extent, what leads to the incredible adaptability and the incredible complexity of computers and the world of code. So, since we're returning to the level of the switch, I would like to return to the switch. We've seen this before in an earlier episode as an example of how code can add layers of complexity to something as simple as a light switch. Of course, a basic light switch, this switch has the functionality of a basic light switch. If you press down, it turns off. If you press up, it turns on. However, we've now added both to the interface. We can take this as an example of what we would call a user interface, the way that the user interfaces with or controls the computer, or in this case, the device. So in this case, the basic interface of the switch has been supplemented with a right and left functionality, which is then used to change the color temperature of the light. So if I go left, it changes the color temperature in one direction. If I go right, it changes the color temperature in another direction. And that's all done through code. And what I'd like to do to get us kind of right down into the technical details of the world of code is to take the language that I've already introduced, basic, beginner's all-purpose symbolic instruction code, which is itself a simplification of the underlying assembly language or machine language that computers work in. That kind of on and off, 1 and 0, basic logic gate world of code. And then it has been extracted into this more English-like language that we can use to control the computer, called BASIC. So I want to take that and build for us a light switch. Once we've built our virtual light switch in BASIC and have learned a little bit about how code works and how that process rapidly ramps up in complexity, I then want to go on and illustrate the further complexity of computer code by rewriting that program in more modern language, Python, on more modern hardware, my Mac computer. This will hopefully give us some insight into how the hardware and the software interact. That is to say, how more capability in the hardware leads both to more functionality and also to more complexity. And from there, I would like to finish with a discussion of how this ever-increasing complexity impacts us as we use code, and how as code is more and more deployed in the world in which we live. So let's dive in and actually do some coding. So here is my Tiracity Color Computer Basic Computer, or rather a simulated version of it. I'm going to use a very simple command, one that was with a part of BASIC from the very beginning, CLS for clear screen. As I always tell my computer programming students, computers are stupid. They do exactly what you tell them to do, and programmers are lazy. So that's why we have all these shortcuts. So CLS clears the screen, and in this case, it clears all the text off the screen and then reprints the prompt OK. Now, this is, of course, not simply a basic computer. This is a color computer. So they put into this version of BASIC some more functionality. So if I do CLS and then I add in parentheses a number after it, it will change the color that I clear the screen to. Now, I can do this because, of course, BASIC is an interpreted language. Any command that I give it, BASIC will actually act on that and execute that command immediately. So if I do CLS0, it will clear the screen black and then immediately mess that up with the OK prompt. But that's okay. No pun intended. Okay, we can now clear the screen in multiple different colors. The other color that matters to me at this moment is CLS5, because that makes a nice white color. So we're going to use CLS0 and CLS5 to turn the screen off and on again. So in order for the computer to remember, in order for us to store this in the computer's memory, you may recall that we need to add line numbers in this. At least we need to do that in this very primitive form of BASIC. So we're starting with line number 10, and we'll start with the screen off. So CLS0 is, of course, off. Now, you may recall that I talked a little bit about variables. Variables are, of course, any kind of letter that you would then use to represent a value that you can store things in. So, classically in math, you have X or Y. In this case, I'm going to use I because I want to store the contents of the INKEY string command. I did cover this one before as well in the very little tiny snippet of code that we have covered so far. So I'm going to do this I string equals INKEY string, which we have looked at before. So INKEY string is the command in Tiracity Color Computer Basic to check the keyboard to see if anything is pressed down. If it is, it stores it now in the variable I string. But this is only a single time command. We want to continuously pull the keyboard for anything that might be pressed. Now, I should also mention that in TRS-80 Color Computer Basic, you needed to distinguish between a numeric variable. So if I used I, for example, that would actually be I'd only be allowed to store numbers in that variable, and a string variable, which could be a character or a string of characters that we usually delineate with quotes, just as we do in real life. If I have a sentence that a character is speaking, I delineate it with quotes. At the beginning and the end of what the character says. So iString is then a variable which is going to contain a string or a character. Okay, so now we've now told the computer to poll the keyboard once, but of course we actually want to do this continuously. So the next line, 30, is going to check the contents of iString, and if they are empty, that is to say they have two quotes with nothing in them, then we're going to go back to line 20 so that we have this potentially infinite loop where the computer is just checking the keyboard, storing the contents in iString, and then as long as nothing is pressed, it will just keep going and going and going and going in this infinite loop, or almost infinite loop. Of course, if you press anything on the keyboard, it's going to jump out of the loop and then go to the next line. So in this case, we're going to add a line 40, and now we're going to say if iString is equal to chrstring, this is another command which I won't go into detail about, but basically every character on the keyboard, every character that was printed out needed to have a value, because of course the computer thinks in numbers, not in letters or characters. So for the up arrow key, when it's pressed, that got assigned the fairly arbitrary value of 94. So we're now going to check to see if the up arrow key was pressed by seeing if the contents of iString, which we now know is not empty, because we've gotten past line 30 where it was checking to see if it was empty, and if it did that, it went back to line 20 and just checked and checked and checked. So now we know that something's been pressed. If it's the up arrow key, then we want to clear the screen with a 5 value. That is to say, make it white, turn it on. Pushing the switch up turns it on. Okay, now, obviously, if it wasn't that, it's not going to, I shouldn't say obviously, if it wasn't that, if that wasn't what was pressed, then nothing that is here at the end of this line will actually be executed. So it'll just skip this line saying, okay, nope, didn't do that, so I'm not going to do this. All right, so now we're going to do the same thing for the down arrow key, which is going to be our down position on the switch. So if iString is equal to chrstring 10, then, that's why I said very arbitrary, right? Then we're going to CLS 0 again. And finally, because we want the computer to do this over and over and over again and just keep going, we're going to add a last line here, go to 20. No condition. If you get to this line, go back to 20 and try and keep checking the keyboard. Okay, this is our program. It's pretty simple. We start with the screen off. We then check to see if key has been pressed in line 20, in line 30. If no key has been pressed, then we go back to line 20 and keep checking. If a key has been pressed, then we don't do that. We go on to line 40 and check to see if the key that has been pressed is the up arrow. If so, we turn the screen on. That is, we clear it to white. And if the key that has been pressed is the down arrow key, then in line 50, we clear the screen to 0. We turn it off, and in line 60, we go back to 20 and start the loop all over again. That's it. Here's our switch. So now if I run this, we start with the screen off. I press the up arrow key on my keyboard. So just to illustrate that here, I've got my keyboard here. I'm pressing the up arrow key, and now the screen is on. Now I'm going to press the down arrow key, and now the screen is off. We have successfully simulated a switch in TRS-80 Color Computer Basic. Now this is just a very basic switch. Again, pun not entirely intended. What we really want to do is simulate not only the on-off functionality of the switch, but also the color temperature. Namely, that when we press the one side, the color temperature gets warmer, and when we press the other side, the color temperature gets cooler. So this immediately introduces two complications. The first complication is actually the limitation of the hardware that we're working with. In TRS-80 Color Computer Basic, we have a grand total of 8 colors. So in order to simulate warmer or cooler, we have, I don't know, really a very limited range of color options. We could, I think the simplest way to do it will be just to say, okay, well, warmer is red and cooler is blue. If we wanted to get a little more complicated, we could have maybe a couple of different shades of red. There does seem to be a red and a bright red and a dark red. And then a couple of different shades of blue, a bright blue and a dark blue. But that's about it. You know, these lights here actually have a wider range of color to them than my TRS-80 color computer did. So this, I think, is actually a pretty good illustration of how hardware matters. Hardware limitations mean that you can do more or less with any given piece of hardware that the computer is controlling. The second complication that we have to deal with here is we now have a need to keep in memory the state of the lighting system. So when it's just on or off, there's no need to keep anything in memory. But now that when it's off, we don't need to keep anything in memory. Because, of course, when it's off, I have no control over the color temperature of the lighting because there is no lighting. However, when it's on, this switch remembers the previous state of the lighting and returns us to that. And then, of course, if I make it warmer or cooler, this switch actually cycles through warm and cool. So I've been representing, for simplicity's sake, left as warm and right as cool. But when it gets warmer or cooler, it then remembers that, and we need to keep that in the computer's memory. So this means that we're going to have to add a couple of different things to our program in order to simulate this slightly more advanced switch. And this actually is a good illustration of the rapidly scaling complexity of code that I have already mentioned in the previous episodes. So in this case, I'm going to create the program myself without walking you through every single stage of the program creation, just to illustrate the complexity of it. Because I want to go from here, as I say, I don't want to make you TRS-80 Color Computer Basic experts or anything like that. I want to go from this example to then another example using different hardware, different software, even a different language, so that we can get a sense, again, of how hardware and software work together and what the limitations of hardware and software, how those matter as we implement this world of code in the physical world that which we actually use to interact with it. All right, I'm going to get some programming done here. All right, and I think that will do it. If we run it now and we turn it on, it's white, and then we go to the right, it's cooler. Or wait, I've got to left is cooler. Okay, whatever. And to the right, it's warmer. And there we go. We're at the warmest setting. And now we're at the coolest setting. And if I turn it off, and then turn it on again, it remembers the state. So yes, we have successfully created the program. Now I'm going to go back and actually demonstrate this fully completed program. Okay. That wasn't as hard as I thought. Okay, so here is our modified program. It actually didn't turn out to be as difficult as I thought it would be. We've added a few lines and extended the program a little bit at the end. So what we've done here now is we still start with the screen off in line 10. We clear the screen to 0, which is black. And then in line 15, we add a temperature variable. So T is going to be equal to 5. 5 is, of course, white, and that is going to be our medium state in our simulation of this switch. So then, of course, in line 20, as we saw before, we check the keyboard to see if a key has been pressed, and then store whatever the result is in iString. And then in line 30, if iString is empty, then a key hasn't been pressed. We want to just wait, and so we go back to 20. And we keep that infinite loop up until a key is pressed. Okay, once the key is pressed, we drop down to the next line, which is line 40, and we test to see if the up arrow key has been pressed. If it is, if it has been, then we clear the screen now not to 5, but to T, the temperature that we have selected. And then in line 50, if we still have, if the down arrow key is pressed, then we clear the screen to black, which is 0. Turn it off. But now in line 60, if the left arrow key is pressed and the temperature is greater than the lowest temperature value that we're going to use. Now we're going to use 3 colors to simulate temperature. And I think I reversed the order here, which we'll see when I actually run the program, but it's not super, I mean, the left and right, warmer, cooler is pretty arbitrary, so I don't think that matters too much. But what we're going to do, just to simulate the color, is we're going to pick 3 colors. So 5, or white, is our medium temperature. The cool temperature is going to be represented by 3. And the warm temperature is, which I think is dark blue. And then the warm temperature is going to be represented by 7, which is light, which is, I think, magenta. So that means that if we are pressing the left arrow key and we're not yet at the lowest temperature or the coolest temperature, then we want to lower the color temperature by 2, because our 3 values are going to be 3, 5, and 7, which differ by 2 either way. So if we want to lower the temperature, we're going to subtract 2. These numbers are fairly arbitrary. I did consider adding another layer of abstraction in, which might have also allowed me to have like gradations of warmth and cool, but I'm trying to keep it simple here. So we're just going with the dark blue, color 3, white, color 5, and magenta, color 7. So if it's higher than the lowest value, then we want to move it in the cooler direction. And then we're going to clear the screen as for that color. Here we're using the colon again to separate 2 commands on the same line. And the nice thing here is that because this is all part of the if statement on line 60, then this will only execute. In other words, we will only subtract 2 and clear the screen again. Both of these commands will only be executed if you're pressing the left arrow key and we're not already at the coolest temperature. Okay, so now in line 70, we do the opposite. So if we press the right arrow key and the temperature is less than the maximum value of 7, then we're going to add 2 to the temperature and clear the screen to that temperature. And then in line 80, we go back to line 20. We don't want to go back to line 15 because that would reset the temperature. We want to remember the temperature. Okay, so hopefully this is now fully functional. I'm going to run it. And of course we start with it off. And now I'm just going to have my controller here. And so now if I turn it on, it starts with the medium temperature, which is white. And now if I press the right arrow key, then it will go to magenta. And if I turn it off and then turn it on again, it remembers the temperature. Now if I press the left arrow key, it goes back to white. And if I press the left arrow key again, it goes to dark blue, which is our coolest temperature. And again, if I turn it off and on again, it remembers the temperature. So, and up, down, off, on, and so on. And now if I keep pressing right, nothing happens because I'm already at the warmest temperature. And then if I go here and now keep pressing left, nothing happens because I'm already at the coolest temperature. And that's our simulation of the switch, the IKEA switch. It's fairly simple. It's necessarily simplified because of the hardware limitations of the TRS-80 color computer. But it hopefully is a simple and comprehensible simulation of this programmed, coded, slightly more complicated light switch. Now, we're not done yet. This is the simple implementation in TRS-80 Color Computer Basic. I now want to take this and redo this with more advanced hardware. That is to say, with a more modern programming language, Python, running on more modern hardware, namely my Mac computer. But not just yet. Well, I've actually shot all of the coding, both for the basic program and the Python program, actually quite a while ago, as you might have noticed from the slightly longer beard in the coding footage. I want to take a break here because, again, my intent here is not to make anybody watching this a programmer. My hope is rather to tease out, as we examine the process of developing code for something as simple as a basic, well, actually slightly enhanced light switch. As I say, the complexity of the process. So we've already encountered a fair bit of complexity here. We have to remember data stored in variables. We have to have conditionals. We have to kind of sort through the process of designing this and even think about what is our user interface? How is the user going to control all this? We're limited by the hardware that we're using. And so we've actually already seen quite a lot of the different layers of complexity that are involved in coding. And I don't want to overwhelm us as we're diving into this. And so I'm going to defer the Python programming exercise to the next episode. And also want to kind of build a bit of reflection around that. And here then I am going to conclude simply by saying, I hope what we've seen so far is, one, code is an abstracted way for us to interact with and control the computer. It's abstracted and simplified from what it used to be, when we actually had to rewire the computer when we wanted to change the programming of the computer, or when we had to do programming on punch cards or in assembly language. This is all done in a language that looks a lot like English, and that is deliberately set up to make it relatively simple to interact with and control the computer. And yet, even as we move from a simple on-off switch to the color temperature version of the switch, we see that this complexity of the program quickly ramps up. We'll see this even more as we move to modern hardware, because as we move to modern hardware, we get more capabilities, but that also means that we have to now pull that complexity into the programming language. But that's for another day. At this point, I think we've seen enough. Probably need to take a break and rest a little bit to take up the more complex version of the code for this very basic light switch that is our model for how we craft and interact with this world of code in which we now live and move and breathe and have our being.